So these are my solutions to the conceptual questions for chapter 26. Um, Basically, here I put a charge and the type of charge that would cause the electric field lines shown. So here, a positive would have field lines pointing away radially from that positive. This point is further away than this, so they're showing the line is shorter. By convention, we normally show stronger fields with lines closer together, but a secondary alternative is longer lines mean a stronger field. Same way down here, this is a negative, so both of these arrows are pointing toward that. Smaller arrow here, same way here. This one's not possible though. So the reason is although you can have arrows pointing radially out from a particular charge, specifically a positive charge, to represent the electric field, you wouldn't have two different strengths emanating from the same point. I think I did number 2 correctly, so black arrow to indicate fields E1 and E2, and then the net electric field here. So notice these are all for A, these are all for B. So for A, it's directly above both positive charges and halfway in between them, so the horizontal components of the field cancel out, the vertical components add up. Here, the horizontal components cancel out, and there's no vertical component. Notice the field caused by Q1 is pointing to the right, though, because it's pointing away from the positive charge, and E2 is pointing away to the left from Q2. For E1, I didn't draw this exactly proportionally, but you definitely can see that for this one, E1 is shorter than E2. The net field is the vector sum of both of them. Same sort of ideas over here. So for 3A and B, I like these. So hopefully you can listen to this explanation. The electric field, to be 0, you need to have fields pointing in opposite directions from each of these two charges. Well, to the left of this large positive charge, the fields caused by this and this are both pointing to the left, so it can't be there. To the right of this smaller positive charge, same way, both net fields are pointing to the right, so it can't be there. In between the two, what you end up getting is an electric field that's pointing opposite directions from these. So your point where the field is 0 is going to be closer to this charge because it has smaller magnitude of charge. How did I know it would be at this point? Because the formula, which again, not on your formula sheet, it is on AP Physics 2, for electric field from a point source is E equals, it could be 1 over 4 pi epsilon sub 0, which is vacuum permittivity. I'm just going to say K, the Coulomb constant, times Q, which is the value of the charge that you're finding the field from, over R squared. So in this case, since it's an inverse square relationship, if I'm twice as far from this, the field strength would be 1/4 the amount as I would be from this. But this has 4 times the charge, so 4 times the charge up here over twice the distance squared give me the same magnitude of field at that spot. Okay, next thing, down here, can't be here. The reason that the electric field can't be 0 in this region is both, although in this region the electric field points different directions caused by this large positive charge and this small negative charge, because the larger charge is closer, they'll never equal out. So it can't be in this region. You'd have a net field smaller than the field caused by this charge, but it would never be 0. In this region, you can't have a field that's 0 because the field caused by this charge is pointing to the right, and the field caused by this charge also pointing to the right in this middle region. And this is the only region where we can have net field as 0, because the electric field caused by the negative charge would be pointing to the left toward the negative charge. The electric field caused by the large positive charge would be pointing to the right away from the large positive charge. And so when I look at this, this has 4 times the charge magnitude as this. So therefore, since we've got the inverse square rule again, this should be twice as far away from the positive as from the negative. So it's 6 units away from the positive, 3 units away from the negative. So I guess I already wrote that over there. For the next one, ranking the strengths of electric field. Here, E2 is greater because the fields are pointing the same direction. E1 is equal to 0. Here, E1 they're adding up. E2 they're subtracting off. So E1 is greater than E2. Here, the magnitude is the same. The field is pointing to the left at point 2. It's also pointing to the left at point 1. Oh, that's interesting. Because this larger arrow is caused by the positive charge, this smaller arrow caused by the negative charge. Here, larger arrow by the negative charge, small arrow by the positive charge. Here, the field here would be 0. Same as what we had here, I guess, for E1. Could have drawn that again, I suppose. Yes, I guess I stopped drawing things down here because it was getting too close in. If you want me to do that, I can. Here, when I turn this straw in the end, I can think about although there will be no electric field inside here if this is uniformly charged. The reason that I could think about it is that because the electric field always cancels out because it's pointing in all different directions. So at the particular center of this, there's no net electric field. When you have this as a conductor, no matter what the shape is, there's no electric field anywhere inside of that. This is a uniform electric field, so by definition, field strengths are the same. I use ratios over here. This is a formula which is on your formula sheet. I've got to look and see which one it is. It's a little bit weird and it's related to Gauss's law, but you can also use it for figuring out field strength inside a capacitor. That's E3. So formula E3. This one I think hopefully okay. Key here, the reason they have the same patterns is the charge to mass ratio is the same, or mass to charge ratio, I guess. So if this was a proton and this was an electron, think about how these patterns might be different. Because a proton and electron have the same magnitude of charge but different masses. Number 9, net force on this pointing to the inside, acceleration always in the same direction as net force, velocity tangent to the path, electric field at this point is caused by this charge. So the electric field at this point is pointing away. It's not saying that the electric field caused by a negative is pointing away. It's saying that the electric field caused by this at this point in space will be pointing away. And whether or not the electron's here, you'd still have the electric field pointing away. So an electric field in space does not depend on there being another charge at that point in space. These things do depend on this charge. If I had something here, if I was asked to figure out the electric field on the proton caused by the electric field on the proton would be pointing toward the electron, be pointing in. Or I guess out from the center of the circle, but toward the electron. And I think that's it.